All right, okay. Thank you everyone for attention my seminar today. The title I'm going to talk that is a nitrogen sensor for In-Situ real-time monitoring nitrate, nitrite, and ammonium in wastewater. Oops. So I will briefly introduce the background for nitrogen sensor and show you the nitrogen sensor development and application in wastewater for high resolution in-situ measurement, and basically show the testing data we got from the sensor test for 1 week field test that held in 2019, the 1 month test in 2019, and the 6 month test. I mean, we have some of the data right now, and very briefly the ongoing work. First, let's take a look why we care about nitrogen. I believe all of us, I mean, in this seminar, we are interested in nitrogen, right? Because the nitrogen pollution, we know that is one of the most widespread pollution in the US, and very likely over the world. It's also a very costly and challenging environmental problem. And we know nitrogen include organic nitrogen and inorganic nitrogen species. For inorganic nitrogen, and we also know include 7 different species, right? Like ammonium, nitrate, and nitrate is a major component for inorganic nitrogen. They are nutrients. They are most species for the nitrogen pollution. So EPA and state recognize the convention septic system is a major source of the nitrogen input for groundwater contamination, also coastal water contamination. And estimate about 20% of homes in the US use septic systems with high nitrogen release. And for the coastal area, generally we say it's a nitrogen sensitive area. It's about 2.6 million cesspool for conventional septic system right now are in use. So that's a big nitrogen contamination source. And so in order to protect the environment, regulators, state regulators, local regulators encourage homeowners to install advanced septic systems. It's also called innovative alternative on-site wastewater treatment systems, we say IA system. Right now it's available. In the past about 10 years, a lot of systems are already installed. But once this IA system is installed, so the function and performance of the IA systems need to be monitored from time to time because the regulators, homeowner, and manufacturers, they need to know the function or performance of the system, right, after installation, and how much nitrogen released to groundwater and how much nitrogen could be reduced, decomposed in the system. Currently, the very common method for the assessment of the IA system is based on a waste chemistry method. We know in the lab analysis, something like the ion chromatic methods or spectrometric method. They're pretty popular. They're very common in lab analysis. This is also a very accurate method certified by EPA. But we know that the lab analysis is not a real-time analysis, right? It's not real-time data. Once the sample was sent to lab, so people probably wait a days, a week to get the data. So the data not reflect real-time condition for the IA systems. Another thing, maybe most important thing is the sample collection. And it needs a tremendous time to collect a sample from the site. And also we know the sample collection, sample transport, and processing prior to the analysis. It needed to be very careful. So our sample needed to properly preserved. Otherwise, all these processes may change the nitrogen species and the concentration. Because a lot of time spent on sample collection and sample testing, so the cost for the lab test is high. but generally each test is about $300. So in order to get the real-time data, reflect the real-time performance of IA system and then reduce the cost for the testing, the sensor is needed definitely for the IA system. Well, for the application of the sensor, basically probably in the three big areas. I mean, it's a potential market opportunity for nitrogen sensor. The first one is in the residential IA with the water system. Okay, so EPA estimates about 2.6 million conventional conventional OWTS system need to be upgraded to IA system. So this is an example for the even for the East Coast area. It's a nitrogen sensitive area from Cape Cod, for example, to Long Island. It's about 0.484 million need to be upgraded to IA systems. On Long Island, right? We have two counties on Long Island. It's about 500,000. The traditional or means conventional WTS need to be upgraded. This is a big market. Another big market that is municipal with the water treatment plant. So it's estimate over 15,000 plant only in the US market. So the third possible, very possible market that is the environmental monitoring market, right? Including the monitoring of the nitrate, nitrite, in surface water, groundwater, and in coastal water. So the nitrogen sensor actually right now, some of the sensors available. So over 1,000 different nitrogen sensors available on market. So all this kind of nitrogen sensor could be classified as two different types. One type is called optical sensors, including the direct UV sensor, including spectrometric sensors for nitrate. For example, it's very popular, right? We know the Grace assay method, or for ammonium based on Indo-Phenol blue method is also very popular. So the advantage for this kind of sensors, the sensitivity is high. That can measure very low concentration nitrate, nitrite, or ammonium. A disadvantage that is the potential interference from with the water. Most of these sensors on the market, that are designed for the freshwater system, from surface water, groundwater, but not for wastewater. It cannot directly deployed in the wastewater system for long-term measurement. Another disadvantage is the cost. The high cost limits their application. Generally, cost about 3,000 to 20,000 based on different brand, different features of the sensors. Another group of sensors that is based on the ion selective electrode for nitrate or nitrite or both. So the advantage for this kind of sensor is a low cost, right? The cost is relatively low in the range of 1,000 to 8,000 range. So this is advantage, but disadvantage that is interference and signal drifting. So this kind of sensor is good if you bring to the field to test that different parameter in the water and then bring back to lab just 1 day or 2 days, field work. But it's not good if you deploy it in the with the water for weeks or for months. So because the signal drifting can definitely ruin the calibration for the long-term measurement. So this is some examples, the sensors on the market. The first one is this one. Let's use a laser pen. This pointer, okay. This one is a newly released sensor by YSI, released last year. This is a LED sensor for nitrate measurement in fresh water. It's pretty sensitive, pretty good. And it's about $7,000 each one. Again, it's for surface water, but not for wastewater measurement. So this sensor is come from the RealTech company. They call Real Nitrate, based on spectrometric method, measure nitrate. It's very sensitive, but again, it's big challenge if we use that for the wastewater measurement. These two sensors, they are ISE sensor. Okay, it's based on the ISE electrode for nitrate or ammonium in this system. It's actually you can see it's different electrode combined inside. So this one from R hydrate company, and this one from In-Situ company. So that means the nitrogen sensor for long-term and low maintenance and the low cost and real-time measurement of nitrate and nitrite ammonium in the IA system is not available yet on the market. So in order to stimulate the development of the nitrogen sensor for the IA system, 4 years ago, in earlier 2017, EPA partnered with the TNC, the Nature Conservancy, the USGS, and others launched the phase 1 of the Advanced Septic System Nitrogen Sensor Challenge. So in the middle of the year, 2017, launched phase 2 of the challenge. That's the sensor prototype testing. So EPA contract Botal to manage the phase 2 of the challenge. And the phase 2, for phase 2 sensor testing that was performed at MassTech, that is the Massachusetts Alternative Septic System Test Center. So all these tests based on the ISO 133, they call it TQAP. This is test quality assurance plan. All this, tests based on this plan. So the EPA have a technical panel. They set up the testing, the schedule, and review the testing data. So they set up a 1 week test, 1 month test, and 6 month test. Okay, so since late 2018, I collaborated with the CCW Center to start work on this kind of sensor. So we attend phase 2 sensor challenge, and we passed the challenge. And right now our sensor is in the 6 months ISO verification testing. So far, run very well. It's already 4 months. So this is the performance goal set up by EPA, by TQAP. The parameter for the nitrogen measurement in the effluent of IA system include ammonium, nitrate, or the other species. This is a minimum requirement, at least the nitrate plus ammonium. The accuracy, that is, should be within 40% of the error. The precision should be less than 40% bias. So this is a requirement. This is not, you can see from analytical chemistry point, so this is not that high requirements, but it's very hard to get this point for the In-Situ long-term measurement. So we got actually this performance goal in 2018, and we start to design our sensor. So we know in the total nitrogen in the effluent of the IA system, including organic and inorganic nitrogen species. But generally, the organic nitrogen species is minor. Most species, a majority species of the nitrogen pollution from effluent of IA system, that is inorganic nitrogen. So we know in the inorganic nitrogen, these 3 species are major, right? Ammonium, nitrate, and nitrite. So we design our objectives for the sensor development. So we're planning to develop a sensor. It's a 1 sensor unit, can measure nitrate and ammonium for both parameters, and In-Situ simultaneous measurement. So this sensor should be with a low cost, should be less than $1,500. Is required by the EPA testing. So should be an easy operation and easy installation in the field, and can be long-term deployed in the wastewater effluent. Should has high reliability and selectivity, and without interference from the wastewater matrix. And based on our reading or different time reading, and with low maintenance. Low maintenance, that means this have a very special requirement for the testing. So we need to meet their requirement. So this is our goal to set up the sensor. So next, actually, I will briefly show you the sensor development and application, but basically testing in the with the water effluent. So this is the first prototype we set up. So we call that the prototype Alpha 1 version, okay? They developed in February 2019 to attend the 1 month field test that at Mestec. So that is a small black box. That is a 1 by 1 by half foot. So I incorporate all the components inside. So you probably can see some light here on. This is the pumps, the 2 parasitic pumps inside. And you can see some bottles over here. That is the chemical reagents and the wastewater bottle. Waste bottle, we collect the waste from the box. The sensor we developed is based on chemical wet chemistry reaction. Okay, it's not reagent-less sensors. It's based on the chemical reagent. So I mean, this is a very first version, but even though they show this sensor show a very good response for both nitrate and nitrite and ammonium in the wastewater. So we have an external computer to control this running. Well, so this is a very beginning and first try. So our sensor didn't pass through the 1 month test at that point. And our sensor show very good accuracy. It's less than 40% error and show good precision. And also meet the requirement for response range and the frequency of the reading. But our sensor didn't meet the requirement for the data management, the maintenance, and the accessible based on their the performance goal. So I mean, by the way, none of the sensor in that time passed the 1 month test. And after that, EPA, the technical panel redesigned the testing, and they start the second cycle, second round test from August 2019. Okay, based on our Alpha version 1, Alpha 1 version. So, and I redesigned the sensor and in 2019. So we add all the components, the chemical reagents, the waste bottle collected, I mean, all this kind of thing included in a single box. You can see this is a single box. The dimension is 1 by 1 by 1 foot. And I mean, the electronic parts I also update inside so that I can remotely operate and download data through Wi-Fi. So this sensor is required to record 168 hour reading, 168 data based on our reading within a week. So with a response range from 2 to 70, this kind of range from low to high nitrate and ammonium response. It's required to continuously deploy it in the water. You cannot, I mean, remove the water or remove the inlet outlet from the water. It should be In-Situ and easily accessible for the maintenance. So in this test, this is 1 week test, 24 lab samples were taken, and for each analysis of the nitrate, nitrite, and ammonium, and compare with the sensor data. So I can show the data later. I just say our sensors function very good in this 1 week test. We passed a 1 week field performance test and won the phase 2 of sensor challenge. So this is an example of the real-time sensor signal. So the red signal, that is the nitrate signal. The blue signal, that is the ammonium signal. So you can see this is a nitrate signal, show higher nitrate, but in the effluent of the IA system, the ammonium is almost 0. This is a real effluent from the IA system. And then the next day, they switch to a tap water. Sweet tap water, and following that, they add they spike the standard with a low concentration, medium concentration, and high concentration of different species. So you can see actually each time they switch the effluent, so the sensor can tell immediately the signal change, right? From hour to hour, they change the species, they change the concentration, the sensor give a reading, different concentration. And the back this actually, the effluent switch to a real effluent of the IA system. Again, the totally 1 week testing. I only show you some example here. It's not 1 week data here. For 1 week testing, after review by Patel and the EPA, so they gave this report. So I just extracted the data from their report. For our sensor reading, for nitrate plus nitrate and ammonium, we have a very good precision. Okay, the precision is lower, less than 5%. We know from analytical chemistry view, less than 5% is perfect. It's ideal condition. This is all 100% in the control range. The recovery, this is the accuracy recovery for nitrate plus nitrite. The average recovery is 93%. Ammonia is about 101% recovery. It's also perfect for both of these parameters. But for our nitrate plus nitrite, so only 52% in there, controls less than 20% error is range. 91% in less than 40% error is range. But then basically overall, that is good, right? So ammonium is 100% in their 20% error range. Based on this data, again, we passed the 1 week test in August 2019. So we were invited to attend the 1 month test that was held actually in December 2019. So this is a comparison between the lab data and the sensor data. So quickly go through it. Okay, this is a 1 week test from day 1 to day 7. Okay, day 1 to day 7. So you can see, let me say the light, let me say this is yellow color. Okay, this is yellow color. That's the lab data for ammonium. What's the sensor? The orange color, this is the sensor data for ammonium. We can take a look at the comparison. So it's the overlap, it's almost overlap all the time, right? It's great with each other very well. But the sensor data of the nitrate, this is the blue line, the blue spot, that's basically lower than the lab data. So this current spot is the lab data. You can see the lab data is higher than our sensor data. It looks like a systematic error. It's not a random error. I would say probably it's my standard concentration or calibration cause this error. Again, after the 1 week test, so all our measurement, all our the function parameter meet their requirement. So whatever the measurement parameter, the data management, and maintenance, accuracy, and frequency, we all meet the criteria of the testing, and we passed the 1 week test, and we move to next phase, next version. That is a 1 month test in December 2019. So during the 1 week test, I found some issues in our instrument. For example, the biofilm formed in the tubing, and because we use that time we use the plastic, all the plastic tubing. I use whatever external and internal the sensors. So I have to update it for 1 month because 1 month testing that more biofilm that may be accumulate. It's easy clog the flow system inside. The sensor, the summary system was redesigned. I use the copper, you can see here is copper tubing. It's anti-biofilling materials. And I add the copper screen at the inlet and outlet of this sampling system to remove the big particles. I also add a big filter inside. We cannot see it. It's inside the big filter to remove the fine particles so that the sensor, the flow channel not clogged. Okay, and also I update the pumps. I use the multi-channel mini pump. It's programmed by Arduino program to run the sensors. So also update the control system. Use a very low cost iPad. It's about $100 the iPad, and remotely operate and download the data. Okay, this is the new looks like version. We call it Alpha 3. Version Alpha 3 for prototype for the 1 month test. So for 1 month test, the sensor is required to run 1 month. It totally read 704 data. Okay, 704 hours reading from day 1 to day 30. And 57 lab sample were taken that time. And measure for both nitrate, nitrite, and ammonium compared with the sensor data. So this is an example for our real signal. like the OneWeek test. So ammonium, that is the orange one, the line, the blue line, that is the nitrate. So you can see here, right? There's something, features about nitrate. It is something I add in the flow system so that I can easily identify which signal is from nitrate, which is from ammonium. Otherwise, so it's very confused which signal come from which species. I added the features so I can easily figure out this signal come from nitrate and nitrite. So I mean, like the OneWeek test, the sensor, whatever, I mean, we add spike the standards or change the effluent, the sensor can tell us a real-time signal change. So that is on this table. This is a very small figure, probably cannot see it. So the sensor results, that is highlighted with yellow. The lab data, that is this two columns, the lab data. So when we take a look actually, this column and this column. Okay, this column, that is the precision for nitrate plus nitrite. This column, this is the precision for the ammonium measurement. We can see it's from day 1 to day 7, this table. Okay, next table, that is from day 8 to day 30, the whole month test. I mean, along the whole month test, we can see actually the precision for sensor performance is really well. It's much better than what I expect. I expected probably less than 10%, but the sensor show us is less than 5%. That is the ideal condition. And for the recovery, the accuracy of the sensor from 1 month test, this is a nitrate plus nitrite recovery. If you take a look at this column from top to bottom, it's all over actually something like 80% to 100%, right? It's ammonium recovery. So basically, I mean, over 1 month, the recovery of nitrite, nitrate, and ammonium is also looks very good. It's all in the 20%. Most are in 20% error range. So this comparison from the lab data is summarized in a figure. This may be easier for us to follow. Okay, so take a look at the blue spot. That is the sensor data for nitrate plus nitrite. The lab data, that's the green spot. Okay, the green spot. So we can, from day 1 actually to day 2, along this time, it's day 1 to day 30, the whole month data. Whenever actually the signal change in the effluent, so the sensor data can reflect the real-time change and match it very well with the lab data. You can see the green data is from the lab, the blue is from the sensor data. It's almost ideal, agree with each other. This is for nitrate plus nitrite. And how about ammonium measurement? The ammonium measurement, the lab data, that is the orange color, it's like the orange color. And so the sensor data, that is a deep orange color. Let me say this is, it's almost also overlap with each other. So here we can see some discrete lab data, but the deep color, that is from the sensor, okay? Basically, most of the signal from both lab and the field, the data sensor reading, very similar, very close. So we summarize all the data in this table. Okay, let's take a look at the panel, the lower panel, the table. This is 1 month recovery data. Again, the average precision, RSD, that's a relative standard deviation for both nitrate plus nitrite and ammonium is less than 5%. It's really good. And the recovery, okay, this is the accuracy. For nitrate plus nitrite, it's almost 100% over a month test. And for ammonium, it's also over 95%. So 96% of the reading is in the ideal, less than 20%. And 100% in there, I mean, the control range is plus minus 40% error, okay, for both nitrate and ammonium. So after review the data by the technical panel of EPA testing, and our data meet all their requirements for the 1 month test. I mean, from the parameter, again, to data management, we can, management is a remote control, remote data transmission, and maintenance as only one maintenance, performance, accuracy, precision, and response range. Okay, it meet all their 1 month test goal. So that means we pass the 1 month test, and then we get to move to the next 6 month test. This is we earn the eligibility for the verification of a sensor technology performance by ISO environmental technology verification standards. So at the cost about 100,000 sponsored by EPA. So this test postponed several times because of the pandemic in 2020. So it started from November 2020. Okay. So this is the sensor performance goal for the ISO test. This is much higher than the screening 1 month OneWeek test. You can take a look at actually the requirement for accuracy is much higher. It's required within 20%, higher than 40%. And the maintenance is no more than quarterly. It means no more than 3 months. So that means our sensor at least runs 3 months, with the water. It's allowed one-time maintenance. So the data recording and the transmission should be totally remote. And the sensor response range should cover from a low to high range for both nitrate and ammonium. The sensor can run actually between 4 degrees and 35 degrees. And they set here frequencies hourly. It's actually, they change it more difficult. That means they change it hourly, daily, or weekly. That means sensor can change any schedule based on the parameter of a customer. Based on that requirement, so we realize our alpha version cannot fulfill their requirement anyway. So our alpha is good for 1 month test, but it's not good for the 6 month test without maintenance. So from the last summer 2020, the CW Center, we started to upgrade our sensor to beta version. So I worked with Brad Dunbar and Brian Feldman for all this kind of thing. We updated the sampling system, the electronic system. So I update the chemical reaction system inside. I add a self-calibration inside for long-term purpose run. And based on our 1 month test, I check all the components inside when I come back to lab, and to figure out some any biofilm or any clog that happened in the 1 month test. So we have to upgrade it. We have to improve that all the parts that had potential problem. And we add a backflash features for this 6 month test, and make sure any plastic part, any rubber tubing, so the wastewater flows through should be cleaned up by the acid or the strong alkaline solution, so that there's no any biofilm formed in my sensor system. Because in the sensor system, the flow tubing I use is very thin. The idea is it's less than 1 millimeter. Okay, less than 1. It's very easy to clog. I can make sure for the long term, like for example, like 3 months test, there is not any particle accumulated in the tubing. So Brian Feldman, he designed the electronic control system. It's show this figure. This is new control system. Integrate, combine all the pump drivers, the controller for valves, the temperature sensor in the single control board. The sensor reading frequency can set up from a lab. We can set up hourly reading. We can set up daily reading. We can set up, each 6 hour reading, something like that. The self-calibration can run automatically based on for a certain number measurement. So this is a new system deployed at Mestec. We have 2 units, a little bit of design inside, and this one I use backflash, use acid, and this one I use base solution. Just check which is better for our next version, the commercial version. So far in both units run very well. Today is almost 4 months, and has continued to run 3 months without any maintenance. The data looks pretty good. I will show you next. So for a prototype beta 1 sensor, we call that sensor as a beta 1 version, has its following features. The first one is remote managing the sampling and data transmission from a lab. We can, whatever, change the frequency sampling, we can download the data from the sensor. We can remotely monitor the sensor unit, each part not working, and which part is not functioning. We can see that from a lab. So it can self-calibrate at each 20 measurement cycles. Like sensor run several days a week, so they automatically calibrate. The cost of the manufacture on all the parts less than $800 plus labor probably less than $1,000 for the sensor unit. I say easy of serviceability. This is easy. Open box, so it's pretty easy. To replace the parts inside. So far, actually, sensor show the free of clog, free of biofilling inside. Even the sensor deployed in the wastewater for 4 months. And another feature is automatically back on after power outage. So we had several time power outage of the sensor. So one is designed by the test procedures, but a couple times it's accident. Power outage, but each time when the power back on, our sensor back on work automatically. And also the Wi-Fi. Sometimes the Wi-Fi not stable, but when Wi-Fi connected, the signal could be, easily we can see the signal from our lab. The sensor also has a suitable response range for wastewater, the nitrate and the nitrite, and ammonium from 2 to 70 milligram nitrogen per liter. I already got 3 month data released from Botel lab data, and because the report is not completely yet, so they don't allow me to release the data. But I can show you the comparison of the data, the month 1, month 2, and month 3. This is overall for month 1 running. This is sensor recovery compared with sensor and precision compared with the lab data. The precision of our sensor run is also like the 1 week, 1 month test. The sensor still is good. It's month 1 data. It's also less than 5%. This is around 2%. Recovery of the sensor data for month 1 compared with the lab data, that is for nitrate, is 97%. For ammonia, it's about 100%. In month 1, totally 52 sample was collected for lab test. So 100% of our sensor reading is in 20% range error, and 94% of the ammonium in this range. That is wonderful. But for month 2 and month 3, we do see something. The sensor data a little bit. I don't want to say worse, but it looks like compared with month 1, the recovery of the nitrate and nitrite is down to 88%, and ammonium is like 97% still. Ammonium looks very good. And from this 2 months, a total 25 sample collect from for lab testing. We have 21. We have 23 in 40% error control range, but we have 21 in the 20% control range. So we are still good. We have 84% in the ideal range. So sensor precision is still good. It's less than 5%. This is a little bit among 5%, but it's after run 3 months, I saw that this is really good. So right now, sensor is still running. Again, it's almost 4 months. I'm planning to perform the second time maintenance, maybe this week or next week. So take a look what's going on. Is there any biofilm formed in the sampling system? Is there any potential clog in the flow system? Right now, I don't know that. I need to open the box, take a look inside what's going on. And so far, so good. The data I download each day, I observe each day is very nice. So ongoing work for us right now for sensor testing. The first one that is complete the 6 months test that will be completed in May, and I could finish all the data processing and the report prepare, and also I could prepare a manual for operation manual for a global. This is called what is Verify Global, this company. We need to upgrade this version, beta 1 version, and so that they sensor can use it in a real world IA system in next few months. So this is in our plan. So we are working on this. Hopefully we'll have new sensor in this month or next month. We can install that in the IA system. I mean, this looks very exciting, right? So one thing we're right now discussing is we design a new sampling system for a real world measurement. Because so the sampling right now we use is good. It's good for the effluent in the IA system, but we don't know is that good for the real world IA system, I mean, in ground. So we need to update that. So we're working on this. And also gonna improve the electronic part, and for the commercialization version. Okay, so probably that happen in a few months. So we're working on this. It's in our plan. And also the last one, ongoing work is business development. And we hope start business properly and contracting manufacturer and so on. All this right now, so it's ongoing. So there's a lot of person and organization involved in this sensor challenge program. I would thank the Center of the Clean Water for Clean Water Technology, CCW Center, the support for this development, the sensor. So the director, Chris Gobler, and scientist, Storwalk, and Bart Dunbar, Frank, Hillary, they all give me a lot of help for sensor development and application. So Brian Feldman from Feldman Consulting, the company designed the new electronic control board for beta version. So this challenge, I mean, sensor development definitely sponsored by, the challenge is sponsored by EPA, led by Maggie. He retired recently. Right now is Curtin and Ian lead the challenge. And George and Brian from Mestech, Nikhil from Patel, Nico, Kevin, and Chris from TNC. They'll give me advice for this challenge. And also my colleagues in the School of Marine and Atmospheric Sciences, Professor Bob Aller and Dr. Cortina Hebron, and my visiting scholar, Dr. Chi, and Mark Wiggin, and Tom Wilson. They all gave me advice and help. So I would also thank our university OTRIL office, Diana and James. They go through, went through all of this, means the technology development, and for our fund application for TAIL fund. And thank you, TNC and partners, and USGS, Mestech, and Suffolk County. Thank you. Thank you for your attention. Now I'll take question.
I have a question. This is Ben Shao. Hi, very impressive talk. Hi. So just in case you would like to upgrade your system with a 5G rather than Wi-Fi, and also have a off-the-grid storage capacity, like using solar panels and battery. And I think the energy center, my energy center, can absolutely help you to do that.
Right, definitely. So we're discussing different plan because the sensor only consume 12 volts. One option is to use a solar panel, but we are thinking about actually a solar panel installed in the homeowner backyard, the front yard. Not sure homeowner like it or not, but we are thinking about this solution. Another solution is for each IA system, they properly has the control panel, I mean electric panel in ground. Because we only use 12 volts, so probably easy incorporate into their unit. we're still this on our plan. It's great. It's great comments, Ben. Thank you very much.
Yeah, and Wi-Fi eventually will be replaced by 5G. So we have actually programmed about the building connectivities, which may be pretty easy. Yeah.
Right. Wi-Fi is definitely the issue. So we won't use Wi-Fi for a commercial version. Probably a cellular 5G, as you said, that is maybe the only choice, only option for us in the future.
Okay. All right.
Yeah. Thank you, Ben.
Sure.
Qing?
Hi, Shep.
Hi, I have a bunch of questions, but I'll start with one. So wastewater is a pretty complex matrix. You showed a cal curve for lab samples. What does it look like if you do standard addition to actual wastewater sample?
So yeah, this sensor design actually, the wastewater, the sample not come into our detector probe. It's separate. That means all the metrics, all the hydrate, cation, anion, or organic matters separated from our signal. There's not any interference from this kind of metrics. So this shows very high selectivity for nitrate and ammonium.
Okay, so after you filter out whatever you're filtering out, it's still a complex sample. I'm wondering what it looks like if you do standard addition to that matrix rather than.
No, I don't standard the addition for the matrix. I mean, there's no other species pass through our filter. The only ammonium, nitrate, and nitrite.
Well, let me ask another one. What about total organic nitrogen? I guess you were not doing that. You can if you oxidatively convert it to nitrate, right?
Right. So the total nitrogen, the organic connection part in the effluent, the IA effluent system generally is minor. It's less than 10% properly. The majority, I mean, that is inorganic. Yeah, we are talking about to measure total nitrogen by using a UV system, the flow system for flow through UV light. I mean, convert organic to inorganic. But maybe it's not nice version. We're thinking about to add different features into the box, the sensor box. But I'm thinking about is that necessary if the organic species is so low, the concentration in the total effluent. Very good comments. Thank you.
I'll ask one more while we're waiting. I was confused about what you said about commercialization. Is this patentable, and are you going to do a startup?
It's patentable. The patent will be filed tomorrow. This is must be filed by tomorrow. I have a provisional patent right now, so that will appear tomorrow. So that means the formal patent should be filed by tomorrow. Right now, I'm working with the attorney on this.
As you said, the market is huge. Are you going to do a startup company?
So I mean, yeah, I mean, we're thinking about this, Chris, and we have a plan, but not. I don't have the detailed plan yet. So we're thinking about this. We're talking about this because we had a type fund. SUNY Research Foundation is planning to support us for the commercialization. It's called the TAF class of 2020, and they require us, I mean, for the commercialization of this product. Yeah, we will have a meeting this afternoon with the university, OTRI our office. So again, I don't have detailed information yet about this.
Yeah, just to offer the comment that there's the idea of creating our own startup and/or having another company license the technology. And so we're both options are on the plate right now. But you're exactly right, Chip. There's a lot of good opportunities.
Great, thanks, good luck.
Thank you.
Go ahead.
So, Jing'an, Qingzhi Zhu, great work. Really, really excited. And obviously excited also for various usages of such systems. And I'm just wondering, when would be a good time for me to include such a system in a proposal to use it in research?
Well, anytime. So Chris and I, we have a startup, me and the seed ground from our school, working on that for the soft water. So we hope we will get a very sensitive version for soft water, fresh water soon. But that's a big challenge because the current version is designed for the wastewater. You know, wastewater, the concentration of nitrate is high. That's above generally 2 milligrams per liter. But for tap water or soft water, it's less than this value. We need to think about the different protocol to realize how to measure so low, like a micromolar level nitrate and nitrite.
Great.
Thank you.
Any further questions? Okay, well, if not, we can all thank Qing for his great accomplishments, great work, great presentation, and we clearly all are waiting to see how far it gets. But great opportunity. So congratulations, Qing, for
Thank you, Chris.
great work you've done on behalf of the SOMAS and Center for Clean Water Technology, and for everybody who tuning in from the outside, thank you for tuning in, and we'll be back first week of April for the next seminar. In fact, I think I might be giving it along with Dr. Arjun Venkatesan. So on monitoring the COVID virus and wastewater at sewage treatment plants. So stay tuned for that, and thank you for your attention, and we'll see you soon.